let's try to get a more feeling about these eigenstates and related measurements. So suppose I again repeat the experiments that I described to you earlier. Here is my atom with some angular momentum. So suppose I again measure L squared first, and there are various possibilities, say L equal to 0, L equal to 1, L equal to 2, etc. So these are the various angular momentum values. Okay, and I take this L equal to 1 beam. Okay, so typically how you do this experiment is you have an atomic beam of particles coming in, and here you have some instrument which separates these particles, incoming particles, according to their angular momenta. And now you have this beam which contains L equal to 1 particles, and then I measure the SZ, and there are 3 possibilities: M equal to 1, M equal to 0, and M equal to minus 1. So it now splits up into 3 beams. I don't care about the other particles. Okay, so now I take this one of these things. Okay, it doesn't have to be M equal to 0. Let's just choose, in fact, we'll do the calculation for general M, and I just now carry out an SX measurement. So SX does not commute with SZ, but it does commute with L squared. So at the end of that measurement, I am going to get a change in the the M values. Okay, so over here, I'm going to get something, but it's not going to preserve the Z component. Now you see the eigenstates of Sx, just like Sz, is going to contain an M equal to 1, M equal to 0, M equal to minus 1, but it's going to be the component of the angular momentum in the x direction. Okay, so it's going to be a completely different set of eigenkets. So I'm going to get an mx equal to plus 1, mx equal to 0, and mx equal to minus 1. But we don't know how those eigenstates are constructed. Okay, they are not the same eigenstates that I have over here. We have not even discussed them yet. Okay, so they are going to be something quite different. But we can still find out, if I make this experiment, I'm going to get all these Sx values. I can just ask the question, what is the average value of Sx with respect to this, okay, eigenstate of L squared and Sz that's coming in. Okay, so just to summarize this experiment, suppose I have this Lm state, which I have generated over here. I have this one, for example, is going to be L equal to 1, M equal to 1 state. Okay, that's how we represent these states. So it's L equal to 1, M equal to 1 state. This one is going to be L equal to 1. Okay, perhaps a comma is nice. M equal to 0 state. And this one is L equal to 1, M equal to minus 1 state. But when I write them like this, it's understood that they are eigenstates of Sz. Now, Sx is a completely different operator, which doesn't commute with Sz and everything. But still, I can find what, on the average, an Sx measurement is going to give me. Okay, so what do I get out of this? So how do I do that? I look at average value of Sx, which is going to be equal to Lm Sx Lm, right? You know how to find average values. That's how I find the average value of the subject. Okay, so this Sx I can easily represent in terms of the L plus and L minus. You see, L plus and L minus are Lx plus or minus I Ly. So if I just take L plus and add it to L minus, the Sy's will cancel, and I get 2Sx. Okay, so if I divide that by 2, I get, divide by 2, I get Sx, right? So let me just put that in here. L M 1 over 2 S, not S, L. Why am I calling these things X? I'm sorry, I just switched to S, which is L, right? S is for spin. Sorry about that. Sorry if I confused you. Okay, I'm just doing this for the angular momentum. Okay, we will be using Sx, but that's going to be something else. Okay, so this is going to be L plus plus L minus, and I have Lm here. So what is this expectation value? 0, right? Why? Because L plus Lm is going to give me Lm plus 1. L minus Lm is going to give me Lm minus 1. But since these things are orthogonal, okay, they are eigenstates of the Hermitian operator. So that is going to give you 0. So that means if I just measure the Lx, okay, the x component of the angular momentum, I have no idea, okay? So I'm going to get either plus h bar, sometimes 0 h bar, sometimes minus 1 h bar, okay? So I'm going to get all kinds of values, and they'll be coming in such that their average value is going to be 0. Okay, so although I may have a very large z component, that doesn't mean that it's going to result in some x component, okay? So let's now do something else. What happens if I instead measure Sx squared? Now,
L squared.
L, yes, thank you. Subliminal guys, start. Okay, thank you. This is also L. So wherever you see an S, replace with an L. Okay. So what is Lx squared? Now, let's just see. So this is going to be L M Lx squared Lm. And what is Lx squared? So it's going to be Lm Lx squared. You know what Lx is? This is just the square of that. So it's going to be 1 over 2, right? L 1 over 4 when I square it. Lx plus L minus squared Lm. That's
L plus minus L minus.
L plus, yes, okay. That means I have entered the state where you have to check my algebra much more correctly because I'm making one mistake per line on the average. Okay, so Lm let me see if I can avoid a mistake this time. 1 over 4 L plus squared plus L minus squared. And then I have an L plus L minus plus an L minus L plus. Okay, I think I'm okay. All right, and now I know what these L plus, L minus, and L minus L plus are, right? They are almost the same except that one has a plus H bar LZ in it. The other one has a minus H bar LZ in it. So when I add them up, the plus and minus H bar LZs are going to cancel. So I'm going to get, check my algebra, LM 1 over 4 L plus squared plus L minus squared plus, okay, 2 of L squared minus LZ squared. Am I okay? Okay. I mean, each one of these terms are going to contribute L squared minus LZ squared. One of them comes with a plus H bar LZ, the other one comes with a minus H bar LZ, which cancel. Okay, so tell me what these things are term by term. There's a 1 over 4. What does L plus squared, what's the average of L plus squared? 0, right? Because this raises this by 2, which will be orthogonal to this one. Okay, so that's going to be 0. What about this one? 0 again, because that lowers by 2. Then I have a 2, and L squared gives me what?
L times L plus 1.
Times H bar squared, right? Okay, so the units is important. H bar squared, L plus 1, and minus?
M times M plus 1 H bar squared.
No, not M plus M.
Oh, M squared.
For LZ, it's just M. M squared, H bar squared. Okay, so that's it. So I'm going to get 1 over 2 H bar squared L plus 1 minus M squared. Yes?
So for the L minus L square minus LZ square, is it bracket or just a commutator?
No, for a commutator you need a comma.
Okay.
If there's no comma, okay, then it's just an expression. Okay, what would be the commutator of L squared with LZ squared, by the way?
0.
0, right? Because LZ commutes with L squared. Okay, so that's what I get. That's the end result of the experiment. So if I measure Lx, I am going to get 0. But if I change my experiment just a little bit, so let me just erase this piece. And now I am measuring L squared, Lx squared. What are the possible values of Lx squared? Well, okay. Obviously, the Lx is going to have the same set of eigenvalue spectrum as Lz, right? It's going to have minus h bar 0, plus h bar, plus 2h bar, etc. So it's going to have all those squares. So let's make it even more specific. So let me just put in a certain state. So I have this, say, one state that's coming in, and I am just measuring Lx. Okay, so Here, what are the possibilities?
1, 0, minus 1.
Okay, so mx is 1, mx is 0, mx is equal to minus 1. So those are the possible measurements that I can get out of Lx, right? Now, I found out that if I find what Lx average is, I get 0. Okay, so apparently I get sometimes 0, sometimes minus 1, sometimes 1, but I get them in such a symmetric fashion that on the average I get 0. Now, what happens if I take the same state, 1, 1, and this time I measure Lx squared? Okay, so now what do I get? Okay, 0 and 1 with the h bar squares. Okay, so this is obviously just the index, but the quantity that you get is either h bar or 0 or minus h bar. And here you are going to get either h bar squared, right, because it's Lx squared, or 0. Okay, so if it's minus 1, you are again going to get h bar squared. So now what is the average value of Lx squared? Now it's what we have found here. Okay, so I'm going to get 1 over 2 h bar squared LL plus 1. What is LL plus 1?
2.
Okay, 2, right? It's 1 times 1 plus 1, so it's 2, minus, what's m squared? 1, right? Because this is the L and M that we are discussing. Okay, so this is L, and that's M. Okay, so minus m squared is 1. Okay, so I get 1/2 h bar squared. So what does that mean? 50% of the time I get this, 50% of the time I get that. So that on the average, it averages to 1/2 h bar squared. And just due to symmetry, you can say that 50% of this is plus h bar, 50% is minus h bar. So we have already deduced the probability distribution here, right? 50% I get 0, 25% I get this, 25% I get that. Okay, so that's how it works out. Okay, let's see what happens when I feed in a 1, 0 state, for example. And measure Lx squared. Again, the possibilities are either I get 0 or I get h bar squared. Okay, so those are the two possibilities as a result of this measurement. Now, what do I get in this case? Lx squared is equal to 1/2 h bar squared, so this part is the same.
2 minus 0.
L plus 1 is 2 minus 0. Okay, so now I get h bar squared. So I get a larger possibility for h bar squared. Why is that? Okay, physically, can you see that?
Because m is the angular momentum in z direction, and when we decrease m, it is possible to increase x.
Okay, so we have the same total angular momentum, same L, but less angular momentum in the z direction. If I have less angular momentum in the z direction, that must go someplace for the total angular momentum to be the same. And where it goes is into Lx squared and Ly squared. Okay?
There's something interesting in this.
Okay, let's hear about that.
When we get 1, 0, the maximum value of L square we can get is h is h bar squared.
Okay.
But the expectation value is also h bar squared.
Okay, very good.
So we must deterministically get h bar squared in there. But we also have a y direction. We must have a mistake.
No, why do you say that?
Because
If-
in here, in here we just know that the LZ momentum is 0, so we can have so the sums of squares of Lx and Ly must be 1.
Okay, so what you are saying is that if this is going to give me an h bar squared all the time, Ly squared must give me h bar squared all the time, right? So Ly squared average must also be h bar squared. So the total Lx squared plus Ly squared is going to be 2h bar squared. But we already know that, right? Because Lx squared plus Ly squared plus Lz squared, which is 2h bar squared, and there's nothing in the z direction. Okay? So it is interesting. But, okay, so it's nice that you try to find gaps in the system. Just work yourselves out. Okay, that's something that I did a lot when I was a student, trying to see if there's something wrong with this analysis. Amazingly, it works out. Okay, so it's quite good. Okay, but now let's look at another sort of thing.
There's another
Yes.
peculiarity that
Okay.
I noticed. When we get a 1, 0, then we deterministically know both Lx and Ly, but that's not quite surprising because the both Lx and Ly commutator are Lz, so when Lz is 0, the commutator vanishes.
Yes.
So
Okay,
this is
so
the instance of entirety.
yes, so so if you look at delta Lx, delta Ly, we know that that must be greater than or equal to h bar, well, okay, 1/2 times the magnitude or commutator of Lx and Ly, right? But this is now Lz, and the expectation value of that, which I have to squeeze here, this thing is 0, okay, for that state. Okay, so again, it works amazingly. Perhaps the 0, state, let's also put in a 0, state. Again, let's try to find out if we can fool the system. Okay, so this time I'm going to put in a 0, state into an Lx squared. Okay, the average of Lx we know is 0 for any state. Okay, so that doesn't matter. But let's look at Lx squared. What do you expect to get?
H bar squared over 2.
Careful.
0.
0, right?
Oh.
Because the total angular momentum is 0. If the total angular momentum is 0, there's no way you can get Lx squared. Okay, so again, the possibilities that you would get in general for Lx like this is a set of mx's, okay, which go from minus something to plus something, but let's just see. Okay, so now we have this Lx squared average is going to be equal to 1/2. I'll just write the equation again. L plus 1 minus m squared. Okay, so it's 1/2 h bar squared 0 minus 0, which gives you 0. Okay, so if you just try to measure a zero angular momentum state, m can only be 0, okay? The z component can only be 0. But also, if you try to measure the angular momentum in any direction, okay, x or y or whatever, you are always going to get 0. Okay, so there's no way out. All right. Okay, so let's do something like this. You see, this is very nice. It's quantum mechanics in miniature. That's what angular momentum is called. Okay, you have just this discrete set of states. It's just a miniature system in which you have a nice set of discrete states, and you can construct these things and find expectation values very easily. All right, so let's see, for example, how we would measure. Again, we say we are measuring L squared. This is my general atomic beam coming in, which contains everything. And here I have an L equal to 0 beam that has separated, 0 angular momentum. I'll pick out L equal to 1 states. Okay, so, and these things I just throw away. L equal to 2 and others. Okay, so there will be others, but I'll take the L equal to 1 state. And this time, measure Lx. Okay, now we say that for L equal to 1, it really doesn't depend on whether you have x or y or z, but you are going to get mx equal to 1, mx equal to 0, mx equal to -1 cases. They are not equal to our, okay, so this is not, for example, represented by 1, 1, okay, because this is our m, which is really equal to mz, okay. We never called it mz, but it is for the z direction. Okay, so the eigenkets that we are writing here are all eigenkets of L squared and Lz. Okay, not L squared and Lx. But now, suppose I take one of these, the stuff, and try to measure an Lz. Okay, now what do I get? Careful. Okay, this is not an, okay. No. Okay, we have to do some calculations. Okay, sometimes I ask a question, but I don't expect it to be answered unless you have studied this material before. Okay, so I have these cases, but I am interested in what is the probability of various cases. Okay, so what's the probability for this case, probability of that case, probability for that case. How would I do it? What is our standard procedure to follow when we are calculating these probabilities?
Express the state of Lx in the Lm basis.
Yes. Okay. So this, whatever this thing here is, okay, for the L equal to 1 case, this is going to be, okay, something which looks like C1, 1, 1 plus C, let's call it 0, 1, 0 plus C minus 1, 1, minus 1. Okay, because these three states now form a complete set of states for the L equal to 1 basis. Okay, so these things now form a complete basis for the L equal to 1. Okay, so L equal to 1 and m basis. So I have to expand it in that basis, and then C1 magnitude squared is the probability of 1. Okay, C 0 magnitude squared is probability of getting 0. C minus 1 magnitude squared is probability of getting minus 1. Okay, so that's our standard procedure. We expand the state in terms of the eigenstates of the LZ, L squared Z, LZ basis, and the expansion coefficients squared are going to give me, excuse me, the various possibilities. Now, to do that, I have to find the eigenstates of Lx, which I don't know yet, right? And it is best to work, let's see how much time we have. Okay, we have time. Okay, so it's best to work in a matrix representation of all these operators so that we can find its eigenvectors and eigenvalues. Okay? So let's move on to that. Let me see which one I want to change. Let's go over here. I'll keep my tables. Okay, matrix representations of angular momentum operators. Okay, so we'll look at that. So what does this mean? Okay, I'll use the basis associated with L squared LZ. Okay, so let me put that down also. Okay, we'll use the basis formed by, okay, eigenstates of L squared and LZ. Okay, what I mean by them, they are just these LM objects. Okay, so that's the basis that I'm going to work in. And the simplest thing to do is perhaps look at those operators. What is the matrix representation of L squared in its own basis? Okay, we know that if we use the basis of the operator itself, or eigenfunctions of the operator itself, we are going to get things which are diagonal, right? So how do we construct this matrix? Okay, it's going to be a big matrix. And the elements of L squared are going to be things like, okay, L prime, M prime on the left, L squared in the middle, L, M. Okay, so this is the L prime, M prime, L, M matrix element of L squared. So on the right-hand side, so let me just put these things down. On the right-hand side, I have Lm. The simplest one that I can put one is over here is 0, 0. And on the left-hand side is going to be 0, 0 again. Okay? So right-hand side, left-hand side. So what do I have more? I have L equal to 1 states, 1, 1, 1, 0, 1, minus 1. And I'll have, okay, so I better put them in same order. Okay, so 1, 1, 1, 0. Okay, 1, minus 1. And then comes L equal to 2 states, but I'm not going to carry this out any further. Okay, so I put L squared in between these things and try to find out what these matrix elements are. So in this case, it's very easy because I know that since this is an eigenkit, I am going to get L prime, M prime, right? L, M, and an H bar squared L, L plus 1, right? And this thing is delta L, L prime, delta M, M prime. So indeed, I get diagonal elements. Okay, so everything is going to be proportional to h bar squared. So let me put that h bar squared out of the matrix. Okay. Now, what is this element 0, 0?
0.
0, right? Because it's L equal to 0 state, so that's 0. So this is the L equal to 0 case. Any other element here that I have is going to be 0, okay? Inner product of 0, 0 with anything like this is going to be 0. So in fact, it's just going to be a diagonal matrix, okay? I keep repeating that, but okay, so only these elements here are going to be non-zero. Everything else is going to be zeros. Okay, well, this is outside my area of analysis at the time. Okay, so I have something like this. So let's look at those diagonal elements. What's 1, 1, L squared, 1, 1?
2 h bar squared L.
Okay, 2 h bar squared. What about this one?
Same.
Same. This one? Same. Okay, so that's our L squared operator. Obviously, it has to go on. What's this element over here for the L equal to 2 case?
6.
6, right? And so on. Everything else are zeros.
And there's a lot of degeneracy.
Hmm?
There's a lot of degeneracy.
Yes, there's a lot of degeneracy because for any value of L squared, we have several values of M that satisfy, okay, that construct the object. Okay, let me try to squeeze in LZ over here. So that's going to be, I shouldn't say equal to, but really representation is some matrix like this. So I have this, let me put these in bold lines. Okay, so this is the 0 piece. Okay, so this is the 0, 0 piece. But then there's going to be a L equal to 1 piece here. Okay, something like that, and so on. Okay, so in this case, everything will be proportional to h bar. So let me put that out. And these are the right-hand sides, 1, 1, 1, 0, 1, minus 1. In this direction, 0, 0, 0, 1, okay, 0, 0, I'm sorry, 1, 1, 1, 0, 1, minus 1. Okay. Now again, I am using the eigenstates of the LZ operator, so I expect only diagonal terms, right? So off diagonal stuff, let me just put zeros. Okay, this just comes from orthogonality, right? So tell me what these things are. What's over here?
0, 1, 0, minus 1.
Okay, slowly so that I can grasp it. Okay, so this is 0. Why? Because LZ is 0, right? It corresponds to M equal to 0. Here, M equal to 1, M equal to 1, so I'm going to get 1 h bar. Here, I'm going to get 0 h bar. And here, I'm going to get minus 1 h bar. Okay? So now, for example, okay, so what I see is that I can talk about these matrices separately. This is the part for L equal to 0. This is the part for L equal to 1. And since they are diagonal, the eigenvectors are very simple, right? Eigenvectors and eigenvalues are very simple. They are already, it's a diagonal matrix. So this matrix has, okay, let's just look at the L equal to 1 part. For the L equal to 1 part, what are the eigenvectors of LZ. Okay, so if I take this to be the matrix representation of LZ, if I multiply it by the vector 1, 0, 0, what do I get? What is that 3 by 3 matrix multiplied by that? No. It's the same thing, right? It's an eigenvector. So it's going to be just 1 h bar times 1, 0, 0. What about LZ? 0, 1, 0.
0.
Okay, 0 times itself. It's an eigenvector again. And finally, LZ, 0, 1 minus, I'm sorry, 0, 0, 1 is what?
H bar 0, 0, minus 1.
Not h bar, minus h bar, right? Because it's a minus 1. Minus h bar 0, 0, 1. Okay, so these are the three eigenvectors. And we determined them trivially because it's a diagonal matrix. Because it's a diagonal matrix, the eigenvectors are going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. For any diagonal matrix, right? Those are the eigenvectors. And these are the eigenvalues. Okay, so yes.
So how LZ for 1, 0, 0, how is the eigenvector?
Okay, you just multiply it with this matrix. Hmm?
Birinci first line corresponds to 0, so
Why?
then we move to
No, I'm multiplying it with this piece. This 3 by 3 matrix, okay? This is the L equal to 1 part. This piece here is the L equal to 0 part. Okay, so I'm just looking at that. So if you want the full vector, if you like, you can put a 0 on the top here. But okay, we'll just be interested in the L equal to 1 part for the time being. Okay, any questions? Excuse me. Okay, now let's do some more algebra. Let's look at the matrix representation of something like L plus. Okay. Now, L plus, let me just remind you that L plus operating on L, M gives you square root of L, L plus 1 minus M, M plus 1. But it also has an H bar, L, M plus 1. Okay? So that's something that we have derived earlier. So let's see what we are going to get. Again, let me just look at the L equal to 0 and L equal to 1 parts. Okay, so this is the L equal to 0 part, 0, 0, 0, 0. This is the L equal to 1 part, which is 1, 1, 1, 0, 1, minus 1, and similarly, okay? 1, 1, 1, 0, 1, minus 1. Okay, so this is the L equal to 1 part. This is the L equal to 0 part. There's L equal to 2 part, etc., which I'm not going to discuss, okay, but it will have the same structure. Okay, so now this time I cannot just say that this I'm expanding in terms of the eigenstates of L plus or L minus because they are not the eigenstates, right? So I have to be careful. So let's see over here. What do I have here? 0, right? Because L plus hitting on this is going to give me 0 because there's no way to raise this anymore. This is an L equal to 0 state, M equal to 0 state. I cannot get a 0, 1 state out of this. Okay? So that's going to give me 0. Okay, so in fact that's that. So I don't have anything over here. In fact, the discussion usually goes in this, okay, analysis by various values of L. Okay, so we do it for L equal to 1, L equal to 2, L equal to 0, whatever. Okay, now what about the L equal to 1 cases?
L equal to 1, again is 0.
Okay, so anything, I cannot say whole L equal to 1 is 0. You have to be careful. Okay, so
L to 1, M
I cannot raise this anymore when I hit it with L plus, right? So as long as this is on the right-hand side of L plus, so what I'm trying to do is I'm going to calculate L prime, M prime, L plus, L, M. So as long as I have an 1, 1 on the right-hand side, I'm going to get zeros, right? Because there's no way to raise a 1, 1 state any higher. So I'm going to get all zeros here. Okay, so when can I get a finite term? When I hit 1, 0 with L plus. What do I have on the left-hand side? 1, 1. Okay, so if it's this object here, but I have to look at what I get for the coefficient. So this is going to give me L0 is going to give me what? Careful.
Square root of 2.
Square root of 2, okay, times the other one, right? So that's that. Okay, and anything else? Oops, I put it on the wrong place. This is 1, 0, 1, 1, no, this is correct, okay? Square root of 2, and everything else is 0. What about 1 minus 1? What does,
You can raise it to 0.
Okay, so I can have it to over here, so the other stuff is 0. Okay, so what do I get for the coefficient?
Again, square root of 2.
Okay, it's again, if you put L equal to 1 and M equal to minus 1, I'm going to get square root of 2. So very nice, I got this expression. Okay, let's do it for L minus also.
L minus is adjoint of L plus, so can't we just take transpose conjugate?
Yes, very clever. Okay, so L minus is L plus adjoint, right? So this is interesting notation. This is a plus, but this is dagger, remember? Okay, so that's the adjoint of that. So that's 0. The diagonals are all zeros. But square root of 2 now moves over here, right? Okay, but as an exercise, I am sure you are all doing your exercises very, conscientiously. Just do this the way we did this, okay, and show that this is indeed the case, okay? So now that I have that, I can finally find out what Lx is. Okay, because Lx is 1 over 2. Okay, by the way, we shouldn't forget the h bars, right? In both cases, I have an h bar here. Okay, Lx is 1/2 L plus L minus. So Lx has a matrix representation which looks like this whole thing divided by, okay, their sum, and divided by 2. So, what do I get? Okay, so again, this is the L equal to 0 part that I'm going to separate out. That's 0 plus 0, that's no problem. Let me not forget the h bar and put it there. And then you see, whenever I add these two objects together, I am going to get square root of 2's, but divided by 1/2, it's going to be 1 over square root of 2. So it will be 0, 1 over square root of, so let me write it like this, 1 over square root of 2, 0, 1 over square root of 2, 0, 1 over square root of 2, 0, 1 over square root of 1 over square root of 2, 0. Okay, so now you see this is already Hermitian, it must be, right? But it's a measurable quantity of x. Okay, now we have found it. Okay, exercise find Ly. Okay. You're going to see that you can get an Hermitian object, but this time you are going to get imaginary pieces because to get Ly you have to divide by I and things like that. Okay? So, as far as these things go, we have determined Lx. So now we are in a position next time, which is one Monday, right? We'll find the eigenvectors of eigenvectors of this object, okay, and then that will enable us to expand the eigenvectors of Lx in terms of eigenvectors of Lz, so that we can look at those probabilities that we slightly motivated with all of this thing. Okay, so I'll let you go.